Today is June 16. Welcome, 11. And these are the topics that I want to cover, except that my road to certification hasn't moved. I applied for the certificate. Well, I applied to be a Qiskit advocate. And if you want to do the same thing, nobody stops you. Let's click there. Okay, the application is open. It will keep being open until July. So who knows? I applied, but what they promise is a certificate. So I decided I'm not going to do anything until I get the certificate. That's kind of procrastination. That's all it is. So it doesn't really work. And next time I'll tell you of the progress. So what I want to talk about though is how to create quantum computing algorithms. And I will divide this talk in two parts. First of all, what are the existing quantum computing algorithms, more on the inside look. We all know that there is a Shor's algorithm because Peter Shor invented it. In fact, Peter Shor is alive and well and is teaching at the university. He is American professor, okay? And you can look at the information about it. But we want to understand a little bit more, at least the intuitive understanding of how that works. That's part number one. That's what I want to do. And part number two, there was an interesting presentation at the Qiskit regular webinar. By the way, the regular webinar is at noon. So you may jump from this one to the next one. But on the other hand, next one is I'm doing the ChatGPT, and maybe you'll jump to that one. In both cases, you have the recording. And I personally, I listen to those recordings when I do something else. It's just because I like to condense the time. And so it's usually when I walk around the block or exercise. Now, that will be the first part. The first part is, let's look at one of the algorithms. Let's look at the intuitive understanding of what it does. But the interesting presentation that was last week on the Qiskit webinar was how can you invent more algorithms? Now, none of that is easy. None of that is ABC, not at all. But on the other hand, we are going to look at it and we will get the first glimpse, the first ideas of the understanding. That is because up until now, when I was teaching this course at this big corporation that I cannot name just in case, but John, he knows, he was in my class. So up until now, I was never touching these ideas. I was saying it's good enough to know what the algorithms do, and it's good enough to be able to apply them. But how do they work? Or more than this, how do you create new algorithms? That would be too much. So now I'm going to attack that. Now, in order to show this to you, and that's, I think, what is good about my webinars, is that it's always technical. I always show something and do something. For that, what I need to do is this. Here I am, and I can cancel that and show you what I'm doing. How does it work? So first of all, I have Conda installed here, and I think there's a way to list all there you are. That's how you list all environments. One of the environments that I have is called exactly that Qiskit. And then I need to switch to this Qiskit. Well, in this case, I am there. So I want to deactivate this. Deactivate By the way, I discovered that maybe I don't hear you. So now I do. Okay, now deactivate. Yeah, I'm back to the whatever environment I was. So let's deactivate more. You cannot deactivate anymore. I'm at the base. And now let's activate to open to Qiskit. So conda activate key. And I always insert this. You know it's not there. It wouldn't do it like this. Now it's on Qiskit. Now I am using this repository, which is, by the way, open. You can get it. And it is mentioned in our run file. So the next step that I do is I'm running Jupyter there. I'm saying Jupyter. Okay, Jupyter Lab. Jupyter Notebook would also work. Either way, if it is installed on your computer, you get it. So that Jupyter command opens a browser for you. Here you are, a browser. And now you can see all that I have in my lab. So what I have is, let's move it a little bit that way, is first, it's very basic ABC. ABC looks like that. Let's look at some of the ABC. Atoms of computations. Now I'm doing this, of course you know this, or maybe you know this, that's why I'm doing it. It is how you build those diagrams. You build a diagram, so essentially you build a computer, a quantum computer just for you, just for this task, and it's called quantum circuit. Then you ask quantum computer or imitation of the quantum computer to run it, and since there is noise on that level of matter, noise in the sense that photons may misbehave, you run it a few times. In this case, you run it 248 probably, or 260, 240, that's probably 300. That's what you run. And you get the same result, and the same result is 0. Okay, let's go away from here. That was ABC. Now we want to do something else. We want to do DEF, that will be here. These are the labs that illustrate how you combine multiple qubits together. We know that the qubits can be in an entangled state, and what one knows immediately the other one knows. That is step number 2. Right now, we're on step number 3. What algorithms there exist that gives you hope that eventually it will be quantum advantage, it will be something very powerful. Here you are. And one of the algorithms is Shor. So that's what I want to look at, starting with that. But then I want to show, well, how do you create new algorithms? That's the plan for today. So first of all, let us look at Shor algorithm. It's right here. And mostly we're concerned with basic understanding at this point. So let's do this. Here's the Shor algorithm. It should all work because all of the packages are installed. I installed them in the Conda environment. Well, let's try that, right? Let's go here. It's a Python notebook, so that should work. And there you are, it's trying to do its work all the time that it shows a star. It's trying to import them. And when it's done, there's not a star, but a number. And in fact, it even printed import successful. So yes, it does work. We can trust that the rest of it will also work. And we can start looking at the problem. Now, the problem that Shor's algorithm solves is breaking long numbers into prime dividers, so finding two numbers that when multiplied give you the large number that they came with. The size of the number should be in the thousands, because that is when it becomes practical, when the encryption that is based on that is unbreakable. And what we want to do is, with our quantum computing, break the encryption. You may remember that today, so far, Shor's algorithm was applied only to divide 15. 15 is the max that it did today. Now, ChatGPT will not know. It doesn't know about the latest. But as far as I remember, that's true. Now, that algorithm really is much bigger, but you need a much bigger computer. So therefore, it is this. Now, how does it do it? That's my next question. Next question is that it reduces the problem further and further. It says, I know how to solve a simple problem, or how I know to solve a similar problem. That's a popular approach, as we know, in math. And the joke that you maybe heard about this already is that what's the difference between how a physicist boils tea and how a mathematician boils tea? So the physicist goes straight to the problem and he puts the kettle on the stove and boils the tea. Okay, and that is the physicist. The mathematician, he oh no, second part, I'm better telling joke. Second part, what if you give the physicist a pot that already has water? He just put it on a boiler. A mathematician is different. If you give him a pot, he pours water in a pot and then he puts it on the boiler. But if you give him a kettle full of water, he pours it out because he says, I know how to solve the problem with an empty kettle. So first of all, I'll pour it out and then I'll put water back in. So that is, who makes the joke? Nobody said. Okay, well, that's our approach here. We are going to reduce this problem of finding the prime dividers into a similar problem, period finding. You have a sequence of numbers. What's the period in this? Then that's not the end, right? Then we will apply it to yet another problem, how to find the dividers. At least I've seen. Yes, okay, thank you, Lawrence. Thank you for the praise of the joke. It's old enough. Okay, but the problem that we're going to solve is this, period finding. And the way I understand it, the intuitive understanding is that we will apply a Fourier transform. That's where it gets a little hairy. Fourier transform is, of course, a mathematical way to take a function and to divide it into a sum of many different other functions. So why would you do it? Well, that's because those functions into which you divide your function, these functions will be sine functions. And sine functions are very well known. So you're saying, I am not going to solve the original problem, but I will divide it into a long series of little sine problems. And these I know how to deal with. That's what we will do. Now, that will change the things because now we have an approximation of our original problem. But we can keep adding functions, the sine functions, with more and more granularity, with less and less weight. In other words, theoretically, this Fourier transform results in an infinite number of functions that together constitute yours. Okay, but you are only taking a certain number, maybe 2000, maybe 200, whatever is enough for your calculation. The result will be that you won't get precisely exactly the numbers you're looking for, but you'll get 2 or 3 different possible answers. Well, these 2 or 3 different possible answers, you will check You will just verify, because it's pretty easy to verify the problem once you got the solution. Once somebody tells you that number divides your original number, you can check it. And if it divides it, great. And if not, then sorry, that was good try. So I think that the Shor's algorithm gives you a few possible answers. It's still up to you to verify that. But you see now that you're shifting the space into a somewhat different area, approximately. Well, to me, that's quite complex. Well, to everybody else, it also was complex. When Peter Shor invented this, then people were calling him from all over the world. And then I think that was before the internet communication. So when they met him at the cafeteria, they would ask, "Hey, Peter, did you really solve this problem? Is that really true?" Well, by now it is, right? So that's the idea. The idea is that in that particular case, you create an approximation of your problem, and that's what it looks like. You take your function, trying to find the period, and divide, or rather break it into a sum of multiple. That's the solution. And after that comes the real implementation. So the lab is open. And you know what, let me verify. Here we are, quantum computing. I just want to verify that the lab is open, and then like some other ones, I didn't close it. So let's check. Here it is. That's my lab, and it is public. Okay, that's what we needed to verify. So you can look at the code yourself. You can run it yourself. I'll be happy if you do. If something doesn't work, then just write to me. But you see here, being able to run it doesn't make sure that you quite understand it. So at first, I was quite satisfied to go to this level. Okay, we see the problem, we understand very approximately how it works, and we see the amazing thing is that yes, here are the results. Now that's a more realistic stuff. It's still running on a simulator, air simulator. But it does add noise, and so you see there are different results. And for different number of tries. Well, that you can verify. That's not a big deal. And of course, there will be exponentials formulas, and there will be a, I would say, number theory here involved. But the end result, it will work. Quite amazing with all the references, you can do it. So even though you don't quite understand this, but you can use it. That is nice, right? But that leaves you with the question, well, what if I need to create my own algorithm? What then? Well, it turns out that a very nice guy recently outlined an approach of how you can have a framework for creating algorithms. Well, obviously that's on the level of PhD, but I think PhD is no big deal. You can do it, or we can do it together. So if you try to read all of that, you can get it. Now, in my case, I store it here. Okay. That's where I store my course. And one of the things that I store there is the documentation. And here it is. That's the paper. The paper does look intimidating. And that is not the first thing that you would read. If you want to know how the algorithms are constructed for quantum computing, then I'll show you the presentation, the slides, and the basic idea. And only then I'll say, okay, now you can really write the paper, because paper, you know, like the Alice in Wonderland says, a long paper without any pictures, that just doesn't go. Who would read such a thing? So I'm closing that, just pointing out that it's there, and show you some of the pictures. So here they are. Maybe I will just open images. Here they are. And we need to start from the beginning. That's the group of people who actually compose the paper together. And that's the problem that they're going to solve. The problem is that they will have a sequence of numbers. Familiar, right? We were just dealing with sequence of numbers in the Shor's algorithm. So however it's represented, but it's just a string of numbers. Okay, but they're going to go more than just Shor algorithm. They're going to use this sequence of numbers as an input, but now they want to create a framework for algorithm creation. That's big, and they're going to do it with divide and conquer. Now, divide and conquer is a familiar idea. That's the idea that says break, let's say you're doing a search, a binary search. So you break the search space into two, and then you apply the same algorithm to half of your search and half of your search. And we all know that binary search makes it in logarithmic time, which is great, right? If it does it in the like regular search is the time, the length of the sequence, and logarithm is much, much smaller. So we achieved what we wanted. We got a great speed up, except that we'll have to do it in the context of quantum computing. So first of all, he talks about divide and conquer, and divide and conquer is simple if you are looking for just one number, because it's either here on the left or here is on the right. But his problem is a bit more complex. To make it a bit more realistic, he is asking, do we have a substring, a given substring within this long string? So if that substring happens to be in the left part, then great, it's just wonderful. And if it is in the right part, also great and wonderful. Well, but what if it's partially here and partially here? That seems like problematic at first glance. Nevertheless, he does find a solution. That's the key. So once he found that solution, he can then explain how his algorithm is constructed and divide and conquer in the quantum paradigm. And I'm not going deeper because as the Russians say, I may be, trying to swim in the deep water, not going deep. And then besides, it would be just too much for now. If, let's say, in the class that I teach, they will want it, actually, I'll have to learn it and tell it. But I think that now it's good enough to explain basically how it works. Well, basically, he then suggests adversary methods and that will divide it into parts, but also take care of the substring that is partially in one place and partially in another. And I want to come to the last few slides, which are, that's the details of how do you increase in subsequence. And that's the summary. So he says, in the end, that is a summary. It works. We tried it. It allows you to do this. And that might seem very theoretical, but then you go back and look at all the algorithms that are already invented, and they're very close to this kind of mathematical problem. So we believe that. We trust him. He did it. He achieved a logarithmic for one group of algorithm, and n to the power of 2/3. Now, n to the power 1/2 would be square root. That already would be a good idea. N to the power 2/3 is nothing spectacular, I would say. But still, and then he talks about what is still open. How do we do it? And all of that. Now, I see that at least one question came up. Yes, right. Stepwise refinement is divide and conquer. Okay, great. And some problems that are not solved. So that is the very, very beginning, but at least it begins to give you an idea of how you will invent new algorithms, that it is doable, it has a potential. And that's what I wanted to achieve. I wanted to show an existing algorithm and also then a framework to creating more. What I want to do now is to look at the other things that I wanted to cover. Okay, number one is that maybe IBM finally did it. Maybe not, but let's look at this article, the famous picture of the president with the computer. Yes. And that happened, I believe, yesterday, yeah, June 23. So they talk about that maybe they have solved. Now, what they do is material handling, right? They create new materials. That's one of the big things that even ChatGPT doesn't claim to be able to do. The only caveat is that they were able to run. They ran on a 127 qubits, quite a complicated algorithm. The only caveat is that it's still a simpler problem than the real physical problem. But they were able to compensate for the errors. So it works in this limited space. And it's one of things where you say, not quite a practical application yet, but it shows you a great potential. That's what you can say this. And another thing that I saw just recently is a philosophy corner. It belongs right there. And philosophy corner comes in is because, as you surely know, everybody uses quantum computing and everybody uses quantum physics in general. That we know. For example, GPS relies on the quantum computing clock. Otherwise, GPS wouldn't work. Well, and GPS everybody knows. But why does quantum mechanics or quantum physics work? That nobody understands. And if you want to go into the history corner, you will see how Einstein said it couldn't work and how Bell said it could work and how 2022 Nobel Prize was exactly for proving that Bell was right and so to say Einstein was wrong. But that is a history why we couldn't come to grips with reality and understand how it works, and we still don't. We have this quantum computing chase. Every country chases another, but we do not understand how it works. That's why I leave it for the end of the class, and in this case, for the end of our talk, that here is an interesting article. That article came very recently, as you see, June 9, and it's not exactly 100% related, but it talks about that the funny thing is that the Eastern philosophy, the Buddhism, always said it. It said that there is no self, meaning that it hurts, but who is hurting? It's not clear. My wife, when I mentioned, she said, of course, everybody knows that. Why? Because when they operate on the brain and they don't have any pain sensitive cells in the brain. So you can operate on the brain and the person is conscious. So, and they do it on purpose. They want to make sure that the brain is still a brain. So when they push something somewhere, the person might move his toe, but he will say, "It's not me who is moving the toe. It's you guys moving the toe." So there is no self, as proven by the operations. What he says, though, is that inside our brain there is no center that is responsible for I am. This famous "I think therefore I am" is false, because who this I? Okay, you can read it. I left the link over there. To me personally, it was interesting because my personal story, by the way, was that I loved mathematics best of all and felt that people should be doing only math, even if you sweep the streets. But at night, of course, you do math. But it turns out that physics is even more interesting than math. That's because it also has the mystical part. So it's my personal thing. I investigated the guy, and you can find all about him. That's this guy at the bottom, I think, or at the top. You can find who he is, and yes, indeed, he is a little bit of a guru talking about philosophy, but he's a PhD in neuroscience, so he has the credentials. I'll leave it right there. Okay, so good. Let's do this. Let's stop sharing the screen. And let's see if there are any questions, any notes, or any desires, because I will not promise 100%, but I may talk about this, what you want to talk about next time. So let me do this. Everybody should be able to chat to everybody. Everyone should be able to chat.
Hey, Mark, I have a question.
Yes, please.
I read in the news recently that Intel is going to be shipping 8-qubit quantum computers to some labs in the US. Do you know anything about it?
I'm sorry, I did not hear the exact question.
So I read in the news this week that Intel is going to be shipping 8-qubit quantum computers to some of the labs in the US. I'm just wondering if you have any information about it.
Well, maybe it is your mic, but I cannot make every word. Do you want to type here a little bit? Right here. By the way, I'm allowed to talk to all the other participants. So are you typing?
Yes.
Okay. It doesn't show here who is typing, who is not, but we'll get your input. Okay, you read that Intel will be shipping 8-qubit systems to some UL labs. Wow. Now, of course, we realize that 8-qubit is a very small computer. But the big news is that you can buy it. To some US labs, we assume US labs, third party, not Intel, right? So Intel kind of democratizes quantum computing and allows you to have a little quantum calculator. No, I haven't heard about this. That is a little bit of a different direction. We so far discussed only IBM and others of the same sort who go into larger and larger computers. But that large computer, nobody buys. You really rent it online, even though one medical lab bought itself a computer. One Cleveland lab buys a computer. I think there was a news about this, and you can find this news on our webinar. But that's interesting. So what are you going to do, Kenneth? Buy it for yourself?
No, just following the news.
No. Okay, but it's still interesting. I will, what if we do a quick search? Yes. Well, it just came out, right? Okay, let's do this. So let's save that link. And let's discuss it next time. So if we go to our outline, I usually make a copy of what happened before and prepare for the next time. And this is next week 23. And the first thing that we will do is let's just, no, it was this one, right? Okay. Thank you for the interesting news, and no, we don't need this intellectual property. Okay. I wasn't sharing, but I did it. So great question. Thank you for that. Any more questions, comments? No, not right now. Okay. So thank you very much for coming. You will all get a recording of what was said. And thank you for pushing me to learn more. You see, that is a complex thing. Now, the next one that I'm doing is ChatGPT. And I'll talk about that on the other one, but there the challenge is not that it is hard. No, the challenge is that it's very easy and something happens almost every minute, but that's a different challenge. So thank you very much all. I wish you a great weekend. Thank you. And I hope we'll talk the next week.